All right, so this is another graph problem, building roads. So what's going on here? We have n cities and there are m roads, and we want to add some new roads such that the cities are all connected, right? That you can get from any city to any other city by following some roads. So, and then we're supposed to say how many roads we need to build, and actually like a specific set of roads that you could build. So for example, in this input, there are 4 roads, and 1 and 2 are already connected, and 3 and 4 are already connected. But we need to connect like the 1-2 group to the 3-4 group. So one way of doing that is to build a road from 2 to 3. Also 1 to 4, or 1 to 3, or 2 to 4. It all works. Yeah, so that's the problem. So how does this work? So what we need to do is figure out sort of the existing groups that the roads are, break things up into, right? The existing components. And the answer is just going to be the number of components minus 1. Because every new road that we add can join 2 components, right? So it'll decrease the number of components by 1, and once we're down to 1 component, that means everything is connected. And by a component, I just mean a set of cities that are, all connected to each other. So that would be enough to find sort of the number of roads, but we actually need to sort of describe them. Right, so that's almost the same as the first problem, if you remember that one, where we were given like a grid and we had to count components. Right, this is very similar, except that we actually need to build the roads. So what does that mean? Well, so it basically just means that we need to find a vertex in each component. So what we can do is, start with 0, right? 0 has some component, and then everything that's not already in a component with 0, just connect it up to 0. Of course, we need to check, basically for every component, pick one vertex and connect it to 0. That's not, the 0 component. That would work. So how can we do this? So this is a good opportunity to look at the UnionFind data structure, which does this. So yeah, actually UnionFind is basically built for solving exactly this problem. This is building roads. I'll do it in Python again. So find x gives the component for x, some particular vertex in that component, and then union xy, combine the components for x and y. Okay, so this is sort of the API for UnionFind. Union doesn't return anything. Find returns a component ID, which is going to be like one of the vertexes. So we're going to pick one sort of special vertex in each component to be the parent, right? The leader of that component, the ID for that component. So how does this work? It's actually very simple code, although it's a little bit, there are some subtleties. So there's some vector, it's like the state of the, do it like this. And make a proper object. Okay, so this is some number of vertices, and it supports these union and find operations. And this is, the internal state, which is basically, well, it's a pointer to sort of your parent in the data structure, right? So the idea is, right, we have all these nodes, and as we connect them with edges, we pick one of them to be the leader, and everyone else in that vertex has sort of arrows, which are lookups in this UF map. And so they, you follow the arrows to get to the root. right? So every node starts out pointing to itself, and then the way find works is that you keep following the arrows until you have an arrow pointing to yourself, in which case you're done. And this also has the so-called path compression optimization, which is, right, like as you add things to a component, you might have like a long chain of arrows, as we'll see when we implement union. And so path compression says, like, if you're here and you want to find out who the root is, right, you follow 3 arrows, but then you just rewrite your arrow so that it points directly to the root. And by the way, as you do that, you'll also end up rewriting this arrow, since you recursively called find on your parent. So the point is that all the find calls sort of redirect the arrows to the root, and this makes it run faster. Without this, it runs in linear time, potentially, for a find operation, and with this, it runs in log time. So the way union works is pretty simple. You get the parents of those 2 nodes, and then you draw an arrow from one to the other, right? So to union 2 nodes, first you find their parents, and then you just have one of the parents point to the other, and now all of them, point here. Notice. So that's it for UnionFind. It's very nice. Let's see how to use it to solve this problem. Okay. So we read in the number of vertices, the number of edges, and then we read in each edge. And every edge, connects the 2 components. So for all the currently existing edges, we just union those things together. And now we want to go through and find everything that isn't already connected to 0 and connect it to 0. And notice that this is like actually mutating UF as we go, so that, like, let's say 5 is not already connected to 0, but 5 is connected to 6. When we hit 5, we're connected to 0, but when we hit 6, it'll already be connected to 0 because we mixed 5 and 0, right? And 5 was already connected to 6. So now we just print the output, which is the number of new edges that we added, right? These are just the edges that we're adding. That should be it. There's like a indexing issue. Given one indexed. Yeah, so we built a new road from 1 to 3, which is not the answer that they chose, but it is a perfectly valid answer. Okay, cool. So that worked. Yeah, so this data structure is the heart of this solution. And this tracks connectivity under edge addition, right? So when we add an edge, we can call union, and then that merges these 2 components so that when we look up anything in either of the components, it'll give us the same ID, which is just, happens to be whichever one you passed in second, basically. But this is arbitrary. By the way, there's another optimization called union by rank, where if you're a little bit more clever, about how you union, you can basically shave off the log factor, and it's inverse Ackermann, which is a very, very slowly growing function. But this is usually fine for programming contests, and log n is very close to n. Yeah, so whenever you add an edge, you union the components, and then you check if something's already connected. If find x is not equal to find y, right? Because this is a component ID for x and y. Then we can add an edge between them and then connect them. Right? That's what adding an edge does. And yeah, print out the answer. So this is sort of the diagram you should have in mind. Right? It's just this UF array is everything's pointing to its parent or boss or whatever, and the root of the component is points to itself. So that's it.